Hello there, so welcome back to the channel and welcome to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. Today is day 74. We'll continue from where we stopped in the course called Sampling in Python. We're actually looking at different sampling methods in Python. So the first chapter got us introduced to what is sampling in Python. We learned the difference between two random sampling and few pseudo random sampling. Then we move to different sampling methods like the simple sampling, the systematic, stratified, and cluster sampling. You can catch all of these on the previous two live streams on the channel. We are moving to what is called sampling distribution in Python. You will learn how to get accuracy of sample statistics using relative errors and measure variation in your estimate by generating sampling distributions. So without further ado, let's cover this chapter 3 and understand the concept of sampling distributions in Python. Let's go. So you have access to all the data sets in the YouTube description. Just go to the YouTube description and download the data set so you can also get your hands dirty by following the link under the description. So let's continue this. So welcome to sampling in Python, customer 3. Also, I've prepared my Jupyter notebook and I've imported the required libraries. You can see. So this was what we did for chapter 1. This was for chapter 1. This was for chapter 2. And this is for chapter 3. Okay, so I have all of that already set up. This is still loading. I'll just refresh it really quick there one more time and double check to make sure my network is working fine. Okay, let's go. So relative errors of point estimates. So these are what we need to cover in this lesson within the next 1 hour.
Let's see how the size of the sample affects the accuracy of the point estimates we calculate. The sample size, calculated here with the len function, is the number of observations, that is, the number of rows in the sample. That's true whichever method we use to create the sample. We'll stick to looking at simple random sampling, since it works well in most cases and it's easier to reason about. Let's calculate a population parameter, the mean cut points of the coffees. It's around 82.15. This is our gold standard to compare against. If we take a sample size of 10, the point estimate of this parameter is wrong by about 0.88. Increasing the sample size to 100 gets us closer. The estimate is only wrong by about 0.34. Increasing the sample size further to 1000 brings the estimate to about 0.03 away from the population parameter. In general, larger sample sizes will give us more accurate results. For any of these sample sizes, we want to compare the population mean to the sample mean. This is the same code we just saw, but with the numerical sample size replaced with a variable named sample size. The most common metric for assessing the difference between the population and a sample mean is the relative error. The relative error is the absolute difference between the two numbers. That is, we ignore any minus signs, divided by the population mean. Here, we also multiply by 100 to make it a percentage. Here's a line plot of relative error versus sample size. We see that the relative error decreases as the sample size increases, and beyond that, the plot has other important properties. Firstly, the blue line is really noisy, particularly for small sample sizes. If our sample size is small, the sample mean we calculate can be wildly different by adding 1 or 2 more random rows to the sample. Secondly, the amplitude of the line is quite steep to begin with. When we have a small sample size, adding just a few more samples can give us much better accuracy. Further to the right of the plot, the line is less steep. If we already have a large sample size, adding a few more rows to the sample doesn't bring as much benefit. Finally, at the far right of the plot, Where the sample size is the whole population, the relative error decreases to 0. Let's explore sample sizes.
Hmm. Okay, let's see how sample sizes actually works. I'm just adjusting my chair a little bit. Okay, let's zoom in a little bit to see that clearly. It says calculating relative errors. The size of the sample you take affects how accurately the point estimates reflect the corresponding population parameter. For example, when you calculate the sample mean, you want it to be close to the population mean. However, if your sample is so small, this may not be the case. The most common metric for assessing accuracy is relative error. This is the absolute difference between the population parameter and the point estimate, all divided by the population parameter. It is sometimes expressed as a percentage. We're going to be using this attrition population, mean attrition, available parameter is labeled as PD, to generate a simple random sample from attrition population of 50 rows, setting the seed to 2022. Okay, let's see. I have my data set here. So I'm using the same data set for this lesson. Let us just continue and see what attrition population actually looks like. So this was the same data set we actually use in chapter 2. Okay, 5 rows and 31 columns. Let's see what we can do with this data set that we have here. To generate a simple random sample from attrition of 50 rows, we want to generate 50 rows, setting the seed to 2022. It's going to be attrition pop dot sample. So generate for 50 randoms. So our n is going to be 50, and our seed, which is the random states, will be equal to 2022. Let's see that. Let's see what this looks like here. If I call on attrition 50 now, I see 50 random samples. So we just generated 15 random rows from our actual data set here. Over 4,000 rows of data. I could just do this and make it a little bit smaller also. You just see 50 random, the first 5 rows. Now it calculates that instruction number 1, right? They say calculate the relative percentage again. This time, okay, this is saying calculate the mean employee attrition in the sample. So mean employee attrition in the employee attrition in the sample. Mean employee we calculate the mean employee of in the sample. We are going to say attrition 50, attrition SRS 50 dot mean. So look at the attrition column of this column rather. Yeah, I'm going to select that column, the attrition column. What is the mean of the attrition column? Dot mean. Then I say calculate the relative error percentage. Between this one and calculate the relative error between these two. Yeah, let me do this in my Jupyter notebook. Calculate the mean employee attrition in the sample. If you look at the mean employee attrition in this sample, I mean is 0.06. That is percent. And let's calculate the relative error between mean attrition 50 and mean attrition population. Interesting. So this relative error, the most common metric is relative error. This is absolute difference between population parameter and the point estimate, all divided by the population parameter. It is sometimes expressed as a percentage. So that's how to calculate it. Let's run the code. Voila. So our relative error is 60%. Let's see it in action here. Hmm. Oh, I don't have this. I don't have access to this. Hold up. I've not defined mean attrition population, which is this actual one here from the actual sample. Let's do that for the population. Let's see that. So the mean attrition of the whole data set, and this is the mean attrition of the 50 samples in the data set. Let's see. When you look at the mean attrition of the when we compare them, it is 62%. Same thing we got here. Great. Now let's say it's now saying you should calculate the relative error percentage again. This time use a simple random sample of 100 rows of artificial population. Oh, there is a sample random sample of 100 rows. Okay. I want to generate 100 rows. Now, okay, want to use simple random sampling here in this scenario. Let me use my glasses real quick. So let's do simple random sampling. So I want to perform the same task, but this time I'm using simple random sampling. I want to calculate the mean. I'm going to calculate the mean of the 100 rows. This is the mean attrition. I want to look for the 100 rows. I want to do mean attrition for D. So let me do this first. Let's copy this and give it a shot in our Jupyter notebook. Okay, now I want to get 100 samples. I have to cut that out. After I get the samples, let's look at what 100 rows of data mean. That will be long. These 100 rows samples of data. Let's cut that down to the first 5 rows as usual. Now let's get the mean of the 100 rows of this attrition column for 100 rows. If I look at the mean attrition for 100 rows, that is like 15%. That is probably half of, you can see. For 50 rows, mean attrition for 50 rows. Look at 50 rows here. You can see for 100 rows, a little bit higher. Okay. I mean, the more the population, the higher the mean. Now let's come back here and say calculate the relative difference between the mean population mean population is going to be, okay, relative error. Let's calculate the relative error again. This is this here. I just change it to the actual. So mean attrition for 50, that'll be mean attrition for 100 now. For 100 minus mean attrition for the population, the mean attrition for the population. That should give us our result now. Ooh, you see now? Let's see this in action in this instance here also. So we get 6.9, and this was giving us 62 before. Sample the best. So as you increase the sample size, the sample mean generally gets closer to the population mean, and the relative error decreases. You can see relative error has decreased. It says as I increase the sample size, the sample mean generally gets closer to the population mean. The sample mean gets closer to the population mean. What's the population mean? The first one, right, population mean here. 0.16. Look at the sample mean here. As we increase the sample size, you can see it gets closer. Okay, interesting. So relative error versus sample size. So the plot shows the relative error in the proportion of employee attritions using simple random sampling for sample size from 2 to 1,470, the size of the population. Click generate plots will select new samples for each sample size and calculate the relative errors again. Which statement above about relative errors and sample size is true? True. It says clicking the regenerate plots will select new sample for each sample size. Mhm. This is fine. So for any given sample size, the relative error between the sample mean and the population mean is fixed at a specific value, no? When sample size is large as the whole population, when the sample is as large as the whole population, the relative error is small, but never zero. Nope. Okay, let's see. If the sample mean is greater than the population mean, relative error can be less than zero. Relative error can never get greater than 100%. For small sample size, this additional entry in a sample can result in a substantial decrease in the relative error. That's correct. So you're relatively great at this. As you increase the sample size, relative error decreases quickly at first, then more slowly as it drops to zero. As you can see here. So the more we increase the sample size, the relative error decreases fast. So we nailed it. Let's create a sampling distribution.
We just saw how point estimates like the sample mean will vary depending on which rows end up in the sample. For example, this same code to calculate the mean cut points from a simple random sample of 30 coffees gives a slightly different answer each time. Let's try to visualize and quantify this variation. A for loop lets us run the same code many times. It's especially useful for situations like this, where the result contains some randomness. We start by creating an empty list to store the means. Then, we set up the for loop to repeatedly sample 30 coffees from coffee ratings a total of 1,000 times, calculating the mean cut points each time. After each calculation, we append the result, also called a replicate, to the list. Each time the code is run, we get one sample mean, so running the code 1,000 times generates a list of 1,000 sample means. The 1,000 sample means form a distribution of sample means. To visualize a distribution, the best plot is often a histogram. Here we can see that most of the results lie between 81 and 83, and they roughly follow a bell-shaped curve, like a normal distribution. There's an important piece of jargon we need to know here. A distribution of replicates of sample means, or other point estimates, is known as a sampling distribution. Here are histograms from running the same code again with different sample sizes. When we decrease the original sample size of 30 to 6, we can see from the x values that the range of the results is broader. The bulk of the results now lie between 80 and 84. On the other hand, increasing the sample size to 150 results in a much narrower range. Now most of the results are between 81.8 and 82.6. As we saw previously, bigger sample sizes give us more accurate results. By replicating the sampling many times, as we've done here, we can quantify that accuracy. Ready to replicate?
Okay, I'm ready. Let's replicate sampling. Create an empty list. Replicating samples. So when you calculate a point estimate, such as a sample mean, the value you calculate depends on the rows that were included in the sample. That means that there is some randomness in the answer. In order to quantify the variation caused by this randomness, you can create many samples and calculate the sample mean or another statistics for each sample. Okay, so let's replicate the provided code so that it runs 500 times, assign the resulting list to a sample mean to sample means to mean saturations. Okay, oh, that's around 500 times. So let's create an empty list. You just open up close brackets. So loop 500 times to create 500 sample means. Ooh, let's create a loop. That's a loop 500 times. So mean attrition dot append. Okay, let's run the code. Oh, the network is. Let's reload the page though. While that is coming up, let's try it here. So I have to append it to mean attritions. Okay, I get some error here. Oh, I've not defined my mean attritions. Mean attrition has to be an empty list. Oh, that's my mean attrition. Got that. And voila, we have the day. So that is the list is going to pass the information to. So mean attrition is an empty list. So let's loop it. So this is how we create the loop. So do a histogram of the mean attrition list with 16 bins. Okay. That means 16 bins. Voila, we have our result there. Let's see how it looks like in Jupyter Notebook. Voila. So this sample we've created, mean attritions, this is the histogram of it. A pleasant replicating by generating the sample statistics many times with different samples, you can quantify the amount of variation in those statistics. Let's ignore this. Mm, so we are trying to complete this data analysis in Python. Then we continue building projects based on the data sets we've worked with so far. Replicating parameters. So the dashboard shows a histogram of the sample mean proportions of employee attrition. There are two parameters, the size of each simple random sample and the number of replicates. It's important to understand how each of these parameters affects the result. Use the parameter slider to explore different values and note their effect on the histogram. Which statement about the effect of each parameter on the distribution of the sample means is true. Okay, let's see. Let's replicate it 100 times. Ooh. Sample size of 100. Replicate it 1,000 times. Sample size of 200. Replicate it. Okay. I'll see the higher the sample, the number of replicate, the closer it forms. And the sample size increases. The range of calculated sample means tends to increase. They're supposed to decrease. Mm, Okay. So it's supposed to decrease. The sample mean is decreasing. And the sample size increases. The range of calculated sample means decreases. As you can see here. Powerful parameter play. As sample size increases, on average, each sample mean has a lower relative error compared to the population mean, thus reducing the range of the distribution, as you can see here. Okay. So let's learn about approximating sampling distributions.
In the last exercise, we saw that while increasing the number of replicates didn't affect the relative error of the sample means, it did result in a more consistent shape to the distribution. Let's consider the case of 4 six-sided dice rolls. We can generate all possible combinations of rolls using the expand grid function, which is defined in the pandas documentation and uses the itertools package. There are 6 to the power 4, or 1,296 possible dice roll combinations. Let's consider the mean of the 4 rolls by adding a column to our data frame called mean roll. Mean roll ranges from 1 when 4 ones are rolled to 6 when 4 sixes are rolled. Since the mean roll takes discrete values instead of continuous values, the best way to see the distribution of mean roll is to draw a bar plot. First, we convert mean roll to a categorical by setting its type to category. We are interested in the counts of each value, so we use .value counts, passing the sort equals false argument. This ensures the x-axis ranges from 1 to 6, instead of sorting the bars by frequency. Chaining .plot to value counts and setting kind to bar produces a bar plot of the mean roll distribution. This is the exact sampling distribution of the mean roll, because it contains every single combination of die rolls. If we increase the number of dice in our scenario, the number of possible outcomes increases by a factor of 6 each time. These values can be shown by creating a data frame with 2 columns, n dice, ranging from 1 to 100, and n outcomes, which is the number of possible outcomes, calculated using 6 to the power of the number of dice. With just 100 dice, the number of outcomes is about the same as the number of atoms in the universe, 6.5 times 10 to the 77th power. Long before you start dealing with big data sets, it becomes computationally impossible to calculate the exact sampling distribution. That means we need to rely on approximations. We can generate a sample mean of 4 dice rolls using NumPy's random.choice method, specifying size as 4. This will randomly choose values from a specified list, in this case, 4 values from the numbers 1 to 6, which is created using a range from 1 to 7, wrapped in the list function. Notice that we set replace equals true, because we can roll the same number several times. Then we use a for loop to generate lots of sample means, in this case 1000. We again use the .append method to populate the sample means list with our simulated sample means. The output contains a sampling of many of the same values we saw with the exact sampling distribution. Here's a histogram of the approximate sampling distribution of mean roles. This time, it uses the simulated rather than the exact values. It's known as an approximate sampling distribution. Notice that although it isn't perfect, it's pretty close to the exact sampling distribution. Usually, we don't have access to the whole population, so we can't calculate the exact sampling distribution. However, we can feel relatively confident that using an approximation will provide a good guess as to how the sampling distribution will behave. Let's sample some distributions.
Okay, let's sample some distribution. So exact sampling distributions. So quantify how point estimates, the sample statistics we are interested in varies. You need to know all the possible values it can take and how often. That is, you need to know its distribution. So the distribution of a sample statistic is called sampling distribution. When we can calculate this exactly rather than using an approximation, it is known as the exact sampling distribution. So let's take a look at another sampling distribution of dice rows. This time we will look at 5 height-sided dice. Okay, okay. There's a function we need to know here. Pandas, NumPy, Matplotlib are loaded with their usual aliases. The expand grid function is also available, which expand a dictionary of key value pairs as its argument. Definition of the expand grid function is provided in the documentation. Okay, what is the expand grid function? Okay, so expand a grid expanding 5 8-sided dice. That is, create a data frame with 5 columns from a dictionary name that want to verify. The row should contain all possibilities for throwing 5 dice, each number 1 to 8. Let's see. Let's see this in action. So I need to import some products for this to work. Let's go back to the top of the, that's good. This will be expand grid function. It's going to be five die. Die one, two, three, four, five. Let's see. One, two, three, four, five. Oh, I want to go somewhere. Voilà, several results here. Oh, let's see this. Okay, now I want to wait now. Voilà, we know this. So we just did eight-sided expand grid. Let's do the same thing here. Ooh. So you say expand grid is not defined. Okay. Let's see how I can create this in this instance there. I need to define the expand grids in my Jupyter notebook here too. So let's do that first. Okay, now let's run this. Voila. So we just define the expand grid function. Though I already imported 8 rows from import products. Interesting. Now our die. Let's move on. So number 2, it now says add a column mean row to dice that contains the mean of the 5 rows as a categorical variable. Okay. Mean row is now going to be, it now contain the 5 rows as a categorical variable. Okay. Dice mean row. The mean of for the 5 rows as a categorical 5 rows. 1, 2, 3, 4, 5. Oh, these 5 rows. I'm having 2 dice mean row here. Oh, okay. Why is dice mean row having 2 dice? Okay, add a column of mean rows and convert to a categorical variable. Okay, interesting. So our first dice mean row is going to convert to a categorical variable. Then our second die mean row. But we have 5 dice row here. It's going to be dice. So then we have a die in 5. Okay, voila. We know it. We have our result here. Voila. We know it there. Let's equate it here. Die 1, die 2, die 1, die 2, die 3. Okay, okay. Uh-oh. Die 1. Oh, doesn't want me to just leave that place empty like that. Okay. Let's die 1, die 2, 3, 4, 5. Then the main roll of each dice. Okay. Create a bar. So we need to create a bar plot now. A bar plot for it. A bar plot of main row. Voila, we have our bar plots. Let's see it here. For the main row. Ooh, nice bar plot. It looks like a bell curve shape. Exactly right. The exact sampling distribution shows all possible variations of the point estimate that you are interested in. Wow, interesting, yeah? Actually replicate the same scenario. So generation approximate sampling. Let's see. So we calculate the exact sampling distribution is only possible in very simple rotations with just 5 8-sided dice. Number the number of possible rows is 8 by 5, which is over 30,000 when the data set is more complicated. So let's see what we can do. In this situation, you can calculate an approximate sampling distribution by simulating the exact sampling distribution. That is, you can repeat the procedure over and over again to simulate both the sampling process and the sample statistic calculation process. And in sample 1 to 8, 5 times the replacements assigned to 5 rows. Okay, let's see what we can do here. On sample 1 to 8, that'll be np dot random. We print the mean of the 5 rows. That'll be 5 rows dot mean. Voila, see. So you just sample 1 to 8 number. We got the so that you sample 1 to 8 without replacements. So duplicate the sampling code 100 times, assigning each result to the list sample means 100. Oh, want to do random sampling here. I'll be for I in in range of 1,000. That's to attach to 1,000 times. Maybe sample mean. Sample mean equals to np.random Let's run the code and see. Ooh, you have an error here. Voila. Great, we nailed it. Let's replicate it here. Okay. Okay, so now plot sample mean 100 as histogram with 20 bins. Okay, that's quite simple. Twenty bins. Voila. Have our result here. Let's see our histogram popping up there. Exact versus approximate. Okay. You've seen two types of sample distribution. Now, exact and approximate. It is really important to understand when each should be computed. Should we always be able to compute the exact sampling distribution directly? Mm, the level sampling. So distribution distinguishing. The exact sampling distribution can only be calculated if you know what the population is and if the problem are small and simple enough to compute. Otherwise, the approximate sampling distribution must be used. Okay, that's when you should use the exacts and the opposites. Let's look at standard errors and central limit theorem. Okay.
The Gaussian distribution, also known as the normal distribution, plays an important role in statistics. Its distinctive bell-shaped curve has been cropping up throughout this course. Here are approximate sampling distributions of the mean cut points from the coffee dataset. Each histogram shows 5,000 replicates, with different sample sizes in each case. Look at the x-axis labels. We already saw how increasing the sample size results in greater accuracy in our estimates of the population parameter, so the width of the distribution shrinks as the sample size increases. When the sample size is 5, the x-axis ranges from 76 to 86, whereas for a sample size of 320, the range is from 81.6 to 82.6. Now look at the shape of each distribution. As the sample size increases, we can see that the shape of the curve gets closer and closer to being a normal distribution. At sample size 5, the curve is only a very loose approximation, since it isn't very symmetric. By sample size 80, it is a very reasonable approximation. What we just saw is, in essence, what the central limit theorem tells us. The means of independent samples have normal distributions. Then, as the sample size increases, we see two things. The distribution of these averages gets closer to being normal, and the width of this sampling distribution gets narrower. Recall the population parameter of the mean cut points. We've seen this calculation before, and its value is 82.15. We can also calculate summary statistics on our sampling distributions to see how they compare. For each of our 4 sampling distributions, if we take the mean of our sample means, we can see that we get values that are pretty close to the population parameter that the sampling distributions are trying to estimate. Now let's consider the standard deviation of the population cut points. It's about 2.7. By comparison, if we take the standard deviation of the sample means from each of the sampling distributions using NumPy, we get much smaller numbers, and they decrease as the sample size increases. Note that when we are calculating a population standard deviation with pandas.std, we must specify DDOF equals 0, as .std calculates a sample standard deviation by default. When we are calculating a standard deviation on a sample of the population using NumPy's std function, like in these calculations on the sampling distribution, we must specify a DDOF of 1. So what are these smaller standard deviation values? One other consequence of the central limit theorem is that if we divide the population standard deviation, in this case around 2.7, by the square root of the sample size, we get an estimate of the standard deviation of the sampling distribution for that sample size. It isn't exact because of the randomness involved in the sampling process, but it's pretty close. We just saw the impact of the sample size on the standard deviation of the sampling distribution. This standard deviation of the sampling distribution has a special name, the standard error. It is useful in a variety of contexts, from estimating population standard deviation to setting expectations on what level of variability we would expect from the sampling process. Let's explore some sampling distributions.
Okay, let's see what sampling distributions are. So population and sampling distribution means one of the useful features of sampling distribution is that you can quantify them. Specifically, you can calculate some statistics on them. Here, you look at the relationship between the mean of the sample distribution and population parameter. Interesting. Let's see that in action. So it says calculate the mean sampling distribution 5, sampling distribution 50, and sampling distribution 500. A mean sample each. Having an error. Okay. Oh, I'm having error. I'm having an error whenever I get my code. Oh, I'm having error. Okay, I've not defined a 500. Uh-oh. I've not defined. Okay, how does sample size affect mean of the sample means? As the sample increases, mm, oh, mind-blowing mean multiplication. Even for small sample size, the mean of the sample distribution is a good approximation of the population mean. Oh, interesting. So I need to check this again. Okay, finally, population and sample distribution. Population and sample distribution. Calculate the standard deviation of this. Okay. This is the final step. Calculating the standard deviation. Oh, what's the error again? I didn't mention MP standard deviation, NPSTD. Finally, this one sample means of 50, and this is the results. Voila. We'll define all of this later. And finally, our last answer. It says, how are the standard deviation of sampling distribution related to the population standard deviation and sample size? We set good standards for standard deviation. The amount of variation in sampling distribution is related to the amount of variation in the population and the sample size. These are another consequences of central limit theorem. Interesting. Okay, so we've covered. Oh, we have one more thing to do. Oh, chapter 4, bootstrap distribution. So continue this on day 75. All right, so that's the end of the live stream for today. So I'm going to continue the final chapter on day 75. All right, see ya. Have a wonderful rest of the day.